Hey guys, let's get started. So over the last several weeks, you've learned a lot about many different learning algorithms, from linear regression to logistic regression to generalized linear models to generative algorithms like GDA and IE-based to most recently support vector machines. What I'd like to do today is to start talking about advice for applying learning algorithms, to teach a little bit about the theory behind how to make good decisions of what to do, how to actually apply these algorithms. And so today, I want to discuss bias and variance. And it turns out, I've built quite a lot of machine learning systems. And it turns out that bias variance is one of those concepts. It's sort of easy to understand, but hard to master. What is it? Lots of those, was it all these board games or sometimes smartphone games say easy to learn, hard to master or something like that? So bias variance is actually one of those things where I've had PhD students, that worked with me for several years and then graduated and worked in industry for a couple years after that. And they actually tell me that, when they took machine learning at Stanford, they learned bias and variance, but as they progress for many years, their understanding of bias and variance continues to deepen. So I'm going to try to accelerate your learning of bias and variance, because I find that people that understand this concept are much more efficient in terms of how you develop learning algorithms and make your algorithms work. So we'll talk about this today, and it'll be a recurring theme that'll come up again a few times in the next several weeks as well. Then we'll discuss regularization and talk about how to reduce variance in learning algorithms, talk about train depth test splits, and then also talk about a few model selection and cross-validation algorithms. Let's see, reminders for today. Problem set 1 is due tonight, 11:59 p.m. And if you are not yet ready to submit it today, late submissions are accepted until Saturday evening, Saturday 11:59 p.m., with the details of late submissions written according to the late day policy written on the course website. So definitely encourage you to submit your homework on time today. If for some reason you're not able to, the late submission, which we don't encourage anyone to take advantage of, but it is written on the course website. Problem set 2 will be released shortly. Actually, I think it's already posted online and is due 2 weeks from now. Yeah, right. And so, okay. So, and what I'm going to do today is talk about the conceptual aspects of this. And if you want to see even more math between these sort of conceptual concepts, at this Friday's discussion section, we'll be covering some of the mathematical aspects of learning theory, such as error decomposition, uniform conversions, and VC dimension. One interesting thing I've learned, really watching the evolution of machine learning over many years, is that machine learning as a discipline has actually become less mathematical over the years, right? So I remember when, machine learning people used to worry about computing the normal equations, right? X transpose X inverse equals X transpose Y. How numerically stable is your numerical solver for solving the normal equations, for inverting a matrix or solving linear system equations? But because numerical linear algebra has made tremendous strides, now we just call a linear algebra routine to invert the matrix or solve linear system equations and kind of not worry about whether it's numerically stable or not. But once upon a time, a lot of my friends in machine learning were reading textbooks on numerical optimization to figure out if your, formula for inverting a matrix or really solving linear system equations was numerically stable. And so one of the trends I've seen is that I think 3 or 4 years ago, to understand bias and variance, there was a certain mathematical theory that was crucial to understanding that. And so I used to teach that in CS229. But we decided, we're constantly trying to improve this class, right? But I decided that mathematical theory is actually less crucial today if your main goal is to make these algorithms work. So we still teach it, but we're doing it in the Friday discussion section, and that leaves more time for the main lecture here to talk more about the conceptual things that I think will help you build learning algorithms, as well as for the newer topics like we'll talk about random forests, decision trees in random forests, and neural networks next week. So anyway, okay. So let's talk about bias and variance. Let's say you have this data set. I'm going to draw the same data set 3 times. Okay, so let's say you have a housing price prediction problem where this is the size of the house and that's the price of the house. You know, it looks like if you fit a straight line to this data, maybe it's not too bad, right? But it looks like if this data set seems to go up and then curve downward a little bit, right? And so maybe this is a slightly better model if you fit a, let's see, so this is if you fit a linear function, theta 0 plus theta 1x. But if you fit a quadratic model, maybe this actually fits the data set a little bit better. Or you could actually fit a high order polynomial. This is 1, 2, 3, 4, 5, 6 examples. So if you fit a 5th order polynomial plus theta 5x to the 5th, then you know, you can actually fit a function that passes through all the points perfectly, but that doesn't seem like a great model for this data either, right? And so to name these phenomenon, the function, assuming you know the one in the middle is what we like, fitting a quadratic function is maybe pretty good, so let's call it just right. Whereas this example on the left, it underfits the data, as in it's not capturing the trend that is maybe semi-evident in the data, and we say this algorithm has high bias. Right? And the term bias, you know, the term bias has actually multiple meanings in the English language. We as a society want to avoid, you know, racial bias and gender bias and discrimination against people's orientation and things like that. So the term bias in machine learning has a completely separate meaning, and it just means that, this learning algorithm had very strong preconceptions that the data could be fit by a linear function. This algorithm had a very strong bias, had a very strong preconception that the relationship between pricing and size of house is linear, and this bias turns out not to be true. Okay, so this is actually a different sense of bias than the other types of undesirable bias we want to avoid as a society, which interestingly comes up in machine learning as well in other contexts. Right, we want our learning algorithms to avoid those types of bias as well. There's a different use of the term. And in contrast, in this curve on the right, we say that this is overfitting the data, and this algorithm has high variance. And the term high variance comes from this intuition that you happen to get these 5 examples, but if you know a friend of yours was to collect data from series 6 examples, if a friend of yours was to collect you know, a slightly different set of 6 examples, right? So if a friend of yours were to rerun the collected slightly different set of houses, you know, right? Then this algorithm will fit some totally other varying function on this, and so your predictions will have very high variance if you think of this as averaging over different random draws of the data. So the variations, if a friend of yours does the same experiment, just a slightly different data set, just due to random noise, then this algorithm fitting a 5th order polynomial results in a totally different result. So that's so we say that this algorithm has very high variance. There's a lot of variability in the predictions this algorithm will make. Okay. So one of the things we'll need to do is identify if your learning algorithm, so when you train the learning algorithm, it almost never works the first time, right? And so when developing learning algorithms, my standard workflow is often to train an algorithm, often train out something quick and dirty, and then try to understand if the algorithm has a problem of high bias or high variance, if it's underfitting or overfitting data, and then use that insight to decide how to improve the learning algorithm. Okay? And I will say a lot more about how to improve the learning algorithm. We'll have a menu of tools that we'll talk about in the next couple of weeks about how to reduce bias or reduce variance of of your learning algorithms. I should mention that the problems of bias and variance also hold true for classification problems. So So let's say that's a binary classification problem. If you fit a logistic regression model to this, straight line fit to the data, maybe that's not great, right? If you fit the logistic regression model with a few nonlinear features, so you have features x1, x2, if instead of using x1 and x2 as features, you use additional features like x1 squared, x2 squared, x1 times x2, x1 cube x2, if this is phi of x, right? And you can have a small set of features you choose by hand, excuse me, probably more features than this, or use an SVM kernel and use an SVM for this problem. Then if you have too many features, then you might actually have a learning algorithm that fits the decision boundary that looks like that. Right? And this learning algorithm actually gets perfect performance on the training set, but this overfits. Oh, excuse me. I meant to make the colors consistent. Sorry, I meant to use red, but you get what I meant. And it's only if you choose somewhere in between, that you get something that seems to be a much better fit to the data. The green line seems to be a pretty good way of separating positive and negative examples that's sort of just right. So similar to, I guess I messed up the color slightly, well, kind of, but similar to these colors here, the blue line underfits because it's not capturing trends that are pretty apparent in the data. The orange line overfits. It's just much too complicated hypothesis, whereas the green line is just right. Okay. So it turns out that in the era of GPU computing and ability to train models with a lot of features, by building a big enough model, so take a support vector machine, if you add enough features to it, if you have a high enough dimensional feature space, or if you take a linear regression model or logistic regression model and just add enough features to it, you can often overfit the data. And it turns out that one of the most effective ways to prevent overfitting is regularization. So let me describe what that is. And excuse me, just finding the right notes. I was reworking today's lecture, so this is new things I've not presented before. Sorry about that. Okay, cool. And regularization is it'll be one of those techniques that won't take that long to explain. It'll sound deceptively simple, but it's one of the techniques that I use most often. I feel like I use regularization in many, many models. So just because it doesn't sound that complicated, or maybe it won't even take that long to explain today, don't underestimate how widely used it is. It's used in, it's not used in every single machine learning model, but it's used very, very often. Right? So here's the idea, which is, let's take linear regression. Right? So that's the optimization objective for linear regression. If you want to add regularization, you just add one extra term here, lambda times norm of theta squared, right? Sometimes you write lambda over 2 to make some of the derivations come out easier. And what this does is it takes your cost function for logistic regression, which you're trying to minimize the squared error fit to the data, and you're creating an incentive term for the algorithm to make the parameters thetas smaller. Okay, so this is called a regularization term. Okay. And it turns out that, let's take the linear regression overfitting example. Right. So, if you set lambda equals 0, then it's just linear regression over the fifth order polynomial features. It turns out that as you increase lambda, lambda to some intermediate value, depending on the scale of the data, let's say you set lambda equals 1, then when you solve for this minimization problem, or this augment problem for the value of theta, this term penalizes the parameters being too big, and it turns out that you will end up with a fit that looks a little bit better, right? That maybe looks like that, okay? And by preventing the parameters theta from being too big, you're making it harder for the learning algorithm to overfit the data. It turns out fitting a very high order polynomial like that may result in value of theta that are very large, right? And then if you set lambda to be too large, then you actually end up in an underfitting regime. Okay? So there'll usually be some optimal value of lambda where if lambda equals 0, you're not using any regularization, you're sort of maybe overfitting. If lambda is way too big, then you're forcing all the parameters to be too close to 0. In fact, actually, if you think about it, if lambda was equals 10 to the 100 or some ridiculously large number, then you're really forcing all the thetas to be 0. Right? If all the thetas is 0, then then you're kind of fitting this straight line, right? So that's if lambda equals 10 to the 100. And this is a very simple function, which is the function 0, right? This function h of theta of x equals 0, right? Approximately 0. This is a very simple function, which you get if you set lambda to be very large. And by dialing lambda between a far too large value like 10 to the 100 compared to a far too small value like lambda equals 0, you smoothly interpolate between this much too simple function of h equals 0 and a much too complex function. Okay. So there is, so that's pretty. So that's pretty much it for regularization in terms of what you need to implement. But if you feel like your learning algorithm may be overfitting, add this to your model and solve this optimization problem, and it will help relieve overfitting. More generally, if you are, let's see. More generally, if you have a, say, logistic regression problem, where this is your cost function, then to add regularization, I guess instead of min, this is a max, right? If you're applying logistic regression, then this was the original cost function. Then you can have minus lambda or lambda over 2, right? It just depends on the scaling of lambda, times the norm of theta squared. And there's a minus here because for logistic regression, we're maximizing rather than minimizing. Or this could be argmax in any of the generalized linear model family as well. But by subtracting lambda times the norm of theta squared, this allows you to also regularize a classification algorithm such as logistic regression. Okay. It turns out that, and I want to make an analogy that where all the math details are true, but we don't want to talk about all the math details. It turns out that one of the reasons the support vector machine doesn't overfit too badly, even though it has, it can be working in infinite, like a, infinite dimensional feature space, right? So why doesn't the support vector machine just overfit like crazy? We showed on Monday that by using kernels, it's sort of using an infinite dimensional feature space, right? So why doesn't it always fit these crazy complicated functions? It just overfits the data set like crazy. It turns out, and the theory is complicated, it turns out that the optimization objective of the support vector machine was to minimize the norm of W squared. This turns out to correspond to maximizing the margin, the geometric margin SVM. And it's actually possible to prove that this has a similar effect as that, right? That this is why the support vector machine, despite working in infinite dimensional feature space sometimes, by forcing the parameters to be small, it's difficult for the support vector machine to overfit the data too much. Okay? The theory to actually show this is quite complicated. It's actually very, it showed that for the constant classifiers where normal W is small cannot be too complicated and cannot overfit, basically. But that's why SVMs work and can work in infinite dimensional feature spaces. Yeah.
Might you ever regularize differently per parameters? Like
Oh, sure. Do you ever regularize per element of parameters? Not really. And the problem with that is, you know what, let me give one more specific example, then come back to that. Right? So it turns out that, so we talked about naive Bayes as a text classification algorithm. It turns out that, let's say you have a text classification algorithm problem, classify spam, non-spam, or classify the sentiment, positive or negative sentiment of a tweet or something. Let's say you have 100 examples, but you have 10,000 dimensional features, right? So let's say your features are these, take the dictionary, a, aardvark, and so on. So 1, 0, 1, right? So let's say you construct a feature like this. It turns out that if you fit logistic regression to this type of data, where you have 10,000 parameters and 100 examples, this will probably overfit the data. Because you have, but it turns out that if you use logistic regression with regularization, this is actually a pretty good algorithm for text classification. And this will usually, in terms of performance accuracy, because this is logistic regression, you need to implement gradient descent or something to solve the good value parameters. But logistic regression with regularization for text classification will usually outperform naive Bayes on a classification accuracy standpoint. Without regularization, logistic regression will badly overfit this data, right? And to explain a bit more, imagine that you have a three-dimensional subspace where you have two examples, then all you can do is fit a straight line, right, for the hyperplane to separate these two examples. But so one rule of thumb for logistic regression is that if you do not use regularization, it's nice if the number of examples is at least on the order of the number of parameters you want to fit. Right, so this is if you're not using regularization. It's nice if, in fact, I personally think that I tend to use the regularization only if the number of examples can be maybe 10x bigger than the number of examples, because that's what you need to have enough information to fit good choices of all these parameters. But that's if you're not using regularization. But if you are using regularization, then you can fit, even 10,000 parameters, right? Even with only 100 examples, and this will be a pretty decent text classification algorithm. Okay. The question you had just now, why don't we regularize per parameter, right? So why don't we, let's see, so I guess instead of lambda norm of theta squared, it would be a sum over j, lambda j, theta j squared, right? The reason we don't do this is because you then end up with, if you have 10,000 parameters here, you end up with another 10,000 parameters here. And so choosing all those 10,000 lambdas is as difficult as just choosing all these parameters in the first place. So we don't have a good way to do this. Whereas when we talk about cross-validation and multi-selection a little bit, we'll talk about how to choose maybe one parameter lambda, but those techniques won't work for choosing sort of 10,000 parameters lambda j. All right, cool question.
Along the same lines, is it important to then normalize your features? Because if some features are have very high mean, then regularization would prefer weights on those features as opposed to.
Yes, you're absolutely right. Yes, thank you. Yes, so in order to make sure that the different lambdas are on the similar scale, a common pre-processing step we use in learning algorithms is take your different features. So for text classification, if all the features are 0 or 1, you can just leave the features alone. But if housing classification, if feature 1 is the size of a house, which I guess ranges from I don't know, 100, how big are the biggest houses? I don't know, like whatever. Let's say houses go from, I don't know, 500 square feet to 10,000 square feet. 10,000 square feet is really, really big for a house, I guess. But the feature X2 is the number of bedrooms, which probably ranges from like, I don't know, 1 to, I guess there's some houses with a ton of bedrooms, but let's say most houses have at most 5 bedrooms, I don't know, right? Then these features are on very different scales, and normalizing them to all be on a similar scale. So subtract out the mean and divide it by the standard deviation to scale all of these things to be between 0 and 1 or between -1 to 1 would be a good pre-processing step before applying these methods. It turns out that this will make gradient descent run faster as well. It's a common pre-processing step to scale each individual feature to be on a similar range of values. Right. Yeah, at the back.
Can we quickly go back to support vector machine not overfitting? Is the reason because you're only looking at a few support vectors when you're maximizing, that's why it's not overfitting? Or is it because the minimizing W squared term functions more like the penalty?
So it's actually both. So just repeat it. Why don't support vector machines ever too badly? Is it because there's a small number of support vectors, or is it because of minimizing the penalty W? I would say the formal argument relies more on the latter. So it turns out that if you look at all the class, of functions that separate the data with a large margin, that class has low complexity, formalized by low VC dimension, which you learned about in Friday's discussion section if you want to come to that. And so it turns out that the class of all functions that separate the data with a large margin is a relatively simple class of functions. And by simple class of functions, I mean it has low VC dimension, which we talked about this Friday. And thus, any function within that class of functions is not too likely to overfit. So it is convenient that support vector machine has a relatively low number of support vectors, but that you could imagine other algorithms that have a very large number of support vectors, but so long as the large margin is still a low complexity classifier that won't overfit. Yeah. All right, let's go next question. Oh, sorry, say that again?
If your model underfits, if your model is underfitting, it has high bias, and the first thing to say, and similarly, if the model overfits, it has high variance, and if you have a model that has more high variance and high bias.
Oh, sure, yes. So is it possible to, yes. So one of the, so in general, models that have high bias tend to underfit, and models of high variance tend to overfit. We use these terms, overfit, high variance, underfit, high bias, not quite, they have very similar meanings, right? To a first approximation, assume they mean the same thing. One thing we'll see later, 2 weeks from now, is we'll talk about algorithms with high bias and high variance. This is, and actually one way to think of high bias and high variance, we'll talk more about this later, is if a data set that looks like this, right? And if somehow your classifier has very high complexity, there's a very, very complicated function, but for some reason it's still not fitting your data well, right? So that'd be one way to have high bias and high variance, which does happen. Right? All right, cool. All right. So to wrap up the discussion on regularization, there's one, so mechanically, the way you implement regularization is by adding that penalty on the norm of the parameters. So that's what you actually implement. It turns out that there's another way to think about regularization. So you remember when we talked about linear regression, we talked about minimizing squared error, and then later on we saw that linear regression was maximum likelihood estimation on a certain generalized linear model using a Gaussian distribution as the choice for the exponential family, as a member of the exponential family. It turns out that there's a similar point of view you can take on the regularization algorithm that we just saw, which is, let's say S is the training set. Right? So given a training set, you want to find the most likely value of theta. right? And so by Bayes' rule, P of theta given S is P of S given theta times P of theta divided by P of S. And so if you want to pick the value of theta, that's the most likely value of theta given the data you saw, then because the denominator is just a constant, this is argmax over theta of P of S given theta times P of theta. And so if you're using logistic regression, then the first term is this, right? And then the second term is P of theta, where this is the logistic regression model, say, right? Or any generalized linear model. And it turns out that if you assume P of theta is Gaussian, right? So if you assume P of theta is follow theta, the pi probability on theta is Gaussian with mean 0 and some variance tau squared I. So in other words, if P of theta is 1 over root 2 pi, I guess this would be determinant of tau squared I, right, e to the negative theta transpose tau squared I inverse. Right. So the Gaussian probability as follows. It turns out that if this is your pi distribution for theta, and you plug this in here, and you take logs, compute the max, and so on, then you end up with exactly the regularization technique that we found just now. Okay? And so in everything we've been doing so far, we've been taking a frequentist interpretation. I guess the two main schools of statistics are the frequentist school of statistics and the Bayesian school of statistics. And there used to be sort of titanic academic debates about which is the right one, but I think the statisticians have gotten together and kind of made peace and go freely between these two more and more these days. Maybe not all the time, but in the frequency school of statistics, we say that there is some data and we want to find the value of theta that makes the data as likely as possible. And that's where we got maximum likelihood estimation, right? And in the frequency school of statistics, we view there as being some true value of theta out in the world that is unknown. And so there is some true value of theta that generated all these housing prices. And our goal is to estimate this true parameter. In the Bayesian school of statistics, we say that theta is unknown, but before you see even any data, you already have some prior beliefs about how housing prices are generated out in the world. And your prior beliefs are captured in a prior distribution denoted by P of theta. So this is called the Gaussian prior. And we say that, and if you look at this Gaussian prior, excuse me, it's quite reasonable. It's saying that before you've seen any data, on average, I think the parameters of theta have mean 0, because I don't know if each theta is positive or negative. So giving the mean 0 seems reasonable. And most things in the world are Gaussian, so we just assume that my prior on theta is Gaussian. So we could debate if this is the right assumption, but it's not totally unreasonable, right? But to say, well, actually I think for the next linear regression problem, I'm going to work on next week, and I have no idea what I'm going to work on, what I'm going to apply linear regression in next week. It's actually not too bad an assumption to say, my prior is Gaussian. Right? And in the Bayesian view of the world, our goal is to find the value of theta that is most likely after we have seen the data. Okay? And so this is called map estimation. which stands for maximum a posteriori estimation. So this is actually the map estimator. I guess the argmax of this, right? Is the map or the maximum a posteriori estimate of theta, which means look at the data, compute the Bayesian posterior distribution of theta, and pick the value of theta that's most likely. Okay? And so one of the things you do in the problem set that was just released is actually show this equivalence as well as plug in a different prior for theta other than the Gaussian prior. You experiment with what if P of theta is the Laplace prior and define and derive a different map estimate algorithm. Okay? All right, good. Yeah, question?
So, like these two optimization problems, and you just showed they like only differ by multiplying by P theta. It's kind of, you also see both of these as like the difference between regularizing and not regularizing.
Wait, sorry, can you say that again?
You just showed that these two optimization problems are kind of the same, except in one you multiply by P of theta, and then you also showed that that's equivalent to regularizing.
Yes.
So it's like the difference between these two can also be seen as the difference between regularizing and not regularizing.
Oh, I see. Yes, can the difference between these two be seen as regularizing versus not regularizing? Yes. So MLE here corresponds to the original algorithm without regularization, and this procedure here corresponds to adding regularization. It turns out that frequency statisticians can also use regularization. It's just that they don't try to justify it through a Bayesian prior. They just say, so if you're a frequency statistician, your job is to wake up and come up with an algorithm to estimate this, true value of theta that exists out in the world. And you can come up with any procedure you want. And as part of your procedure, you can add a regularization term. I think a lot of these debates between frequencies and Bayesians are more philosophical. I think as a machine learning person, as an engineer, I don't really, I think the philosophical debates are lovely, but I just like my stuff to work. So frequencies can also implement regularization. It's just that they say this is part of the algorithm they invented rather than derived from a Bayesian prior. All right, cool. So, let's talk about, so in a discussion on regularization and choosing the degree of polynomial, right. So let's see. Let's say I plot a chart where on the horizontal axis I plot model complexity. So how complicated is your model? So for example, to the right of this curve could be a very high degree polynomial. Right? And what you find is that as you increase model complexity, your training error, if you do not regularize, right? So if you fit linear function, quadratic function, cubic function, and so on, you find that the higher the degree of your polynomial, the better your training error. Because a fifth order polynomial always fits the data better than a fourth order polynomial if you do not regularize. But what we saw with the original picture was that the ability of the algorithm to generalize kind of goes down and then starts to go back up, right? And so if you were to have a separate test set and evaluate your classifier on a set of data that the algorithm hasn't seen so far, so measure how well the algorithm generalizes to a different novel set of data, then if you fit a linear function, then this underfits. If you fit a fifth order polynomial, this overfits. And it's somewhere in between right? That is just right, okay? And this curve is true for regularization as well. So say you apply linear regression with 10,000 features to a very small training example. If lambda was much too big, then it will underfit. If lambda was 0, so you're not regularizing at all, then it will overfit. And there will be some intermediate value of lambda that's not too big or not too small that balances overfitting and underfitting. Okay? So what I'd like to do next is describe a mechanistic, actually a few different mechanistic procedures for trying to find this point in the middle. Right? And so so given a data set, what we'll often do is take your data set and split it into different subsets. And a good hygiene is to take the data and train, dev, and test sets. So if you have, say, 10,000 examples, right, and you're trying to carry out this model selection problem. So for example, let's say you're trying to decide what order polynomial you want to fit. Right? Or you're trying to choose the value of lambda. Or you're trying to choose the value of tau. That was the bandwidth parameter in locally weighted regression that you saw in the problem set, that we saw with locally weighted regression. Right? So, or you're trying to choose the value C in a support vector machine. So remember, the SVM objective was actually this, right, with the subject to some other things. But for the L1 non-soft margin that we talked about on Monday, you're trying to minimize the norm of W, and then there was this additional parameter C that trades off how much you insist on classifying every training example perfectly. Right? So whether you're trying to make, whichever of these decisions you're trying to make, how do you choose a polynomial size, or choose lambda, or choose tau, or choose parameter C, which also has this bias variance trade-off. There will be some values of C that are too large and some values of C that are too small. So here's one thing you can do, which is let's see. So split your training data S into a subset, which I'm going to call the real training set, S subscript train, and then some subset, which I'm going to call S subscript dev, and dev stands for development. And then later we'll talk about a separate test set. And so what you can do is train each model. And by model, I mean option for the degree of polynomial. On S train. So if you're evaluating a menu of models, right? So let's say this is model 1, model 2, and so on, up to model 5, up to some number. Then you can train each of these models on the first subset of your data, and then get some hypothesis. Let's call it HI. And then measure the error on SDev, which is the second subset of your data called the development set, and pick the one okay. So rather than, I want to contrast this with an alternative procedure, right? So we have two subsets of the data. I'll talk about test set later. training set and development set, and after training first order polynomial, second order polynomial, third order polynomial on a training set, evaluate all of these different models on a separate held up development set, and then pick the one with the lowest error on the development set. Okay. By the way, one thing to not do would be to evaluate all these algorithms instead on the training set, and then pick the one with the lowest error on the training set. Right? Why not? What goes wrong if you do that? Yeah, right. You just overfit. Why will you overfit?
You're minimizing the error on what you were training, so you have an incentive to go away the higher or the equal number when it's not good.
Yeah, yep, cool, right. So if you use this procedure, you always end up picking the fifth order polynomial, right? Because the more complex algorithm will always do better in the training set. So if you do this, this will always cause you to say, let's use the fifth order polynomial or the highest possible order polynomial. So this won't help you realize in the housing price prediction example that the second order polynomial is a better fit to the data, right? Does that make sense? And that's why for this procedure, if you evaluate your model's error on a separate development set that the algorithm did not see during training, this allows you to hopefully pick a model that neither overfits nor underfits. And in this example, hopefully you find that it'll be the second order polynomial, right? The one that's just right in between that actually does best on your development set, okay? All right. Now, and then, you know, if you are publishing an academic paper on machine learning, then this procedure has looked at the training set as well as the development set, right? So this procedure, this piece of code is, you know, is tuned its decisions, is tuned the parameters of the training set, and is tuned the decision on the degree of polynomial to the depth set. And so if you want to know, if you want to publish a paper to say, oh, my algorithm achieves 90% accuracy on this data set, it's not valid to report the result on the depth set because the algorithm has already been optimized to the depth set. In particular, information about what's the best degree polynomial to choose was derived from the depth set, from the development set. And so if you're publishing a paper or you want to report an unbiased result, evaluate the algorithm on a separate test set, S-test, and report that error, okay? And so if you're publishing a paper, it becomes considered good hygiene to report the error on a completely separate test set that you did not in any way, shape, or form look at during the development of your model, during the training procedure. Okay, does that make sense? Yeah.
Are dev and test set errors generally different by much?
Our dev and test set error is generally different by much. It depends on the size of the data set. And so it turns out that actually, let me give an example. Actually, so let's say you're trying to fit a degree of polynomial, right? And you want to choose right the dev error. So you can fit the first, second, third, fourth, fifth degree polynomial. And so after fitting all of these, let's say that the squared error, right, to just use round numbers, is 10, 5.1, 5.0, 4.9, you know, 7, 10, and so on, okay? Just to use round numbers for illustrative purposes. If you're using the dev error to pick the best hypothesis, to pick the best classifier, you would say that using a fifth order polynomial gets you 4.9 squared error, right? But did you really earn that 4.9 squared error, or did you just get lucky? Because there is some noise, and so maybe all of these actually have error that close to 5.0, but some are just higher, some are just lower, and you just got a little bit lucky that on the dev set this did better. Which is why if you look at your dev set error is a biased estimate, right? And so whereas you have a very large test set, if it's a very large test set, maybe the true numbers are 10, 5, 5, 5, 7, 10 are your actual expected squared errors. It's just that because of a little bit of noise, you got lucky and you reported 4.9. And so this would be a bad thing to do in an academic paper, right? Because it's of what you earned was an error of 5.0. You didn't earn an error of 4.9. It's just that because you're overfitting a little bit to the depth set, you chose the thing that looked best for the depth set, but your algorithm didn't actually achieve that error. It's just because of noise. Okay? Now so it's considered good practice to report. So reporting on the depth error isn't really a valid, unbiased procedure. Yeah, is there a question?
Just to continue the analogy, so say you publish a paper, then next year comes around, you start developing models. Would you then test the same data set, or you basically collect new test sets? Because then would you have a risk of sort of like indirectly so looking at the test set that was before that? The models you publish a paper a year goes by, in this data set, you could get better test errors. It may just be that directly.
Yeah. So one of the, just to research it, yes, you're right. One of the problems with some of the machine learning benchmarks that people worked on for a long time is there's this unavoidable mental overfitting. The people gotten to use the data set and everyone's working on the same, trying to publish the best numbers in the same test set. So the academic community on machine learning does have some amount of overfitting to the standard benchmarks that people have worked on for a long time. And this is an unfortunate result. When the test set is very, very large, the amount of overfitting is probably smaller. But when the test set is not big enough, then the overfitting result can cause sometimes even research papers to publish results that are probably overfit to the data set. Right? And so I think there's actually one standard academic benchmark was a data set called CFAR. It's quite small. There's actually a very interesting research paper analyzing results on CFAR, arguing that some fraction of the progress that was made was actually perhaps researchers unintentionally overfitting to this data set. Okay. Oh, and by the way, one thing I do when I'm building, production machine learning systems, so when I'm shipping a product, right, I just want to build a speech recognition system and just make it work. I just want to, and if I'm not trying to publish a paper, I'm not trying to make some claim, sometimes I don't bother to have a test set, right? So, and it means I don't know the true error of the system sometimes, but I'm very conscious of that. If I don't have a lot of data, sometimes I'm going to decide to just not have a test set, and it means I just don't try to report the test set number. I can report a depth set number, which I know is biased, and I just don't report a test set number. Don't do this if you're publishing your academic paper, right? This is not good if you're publishing a paper or making claims on the outside, but all you're doing is building a product and not writing a paper. This is actually okay. Yeah.
When you're creating the three splits of the data set, do you tend to just do it by random sampling? And if so, is that more difficult when you have a more limited data?
Yeah. Okay. Good. Let me get to that. Good. So the next topic about setting up a train depth test split is how do you decide how much data should go into each of these three subsets? I can tell. So let me just tell you the historical perspective and then a modern perspective. Historically, the rule of thumb was you take your training set, right? Take your training set S, and then you would send. One rule of thumb that you see a lot of people refer to is 70% train, right? 30% test. This is one common rule of thumb that you just hear a lot. Or maybe you have, if you don't have a depth set, if you're not doing model selection, if you already picked the model, not regularizing, or maybe you have people use 60% train, 20% dev, 20% test, right? So these are rules of thumb that people use to give, and these are decent rules of thumb when you don't have a massive data set. So if you have 100 examples, maybe 1,000 examples, maybe several thousand examples, I think these rules of thumb are perfectly fine. What I'm seeing is that as you move to machine learning problems with really, really giant data sets, the percentage of data you send to dev and test are shrinking, right? And so here's what I mean. Let's say you have 10 million examples, decent size, not giant, but like a reasonable size. So let's take this. This is actually a pretty good rule of thumb if you have a small data set. If you have 500 examples, this is a perfectly fine rule of thumb to use. But if you have 10 million examples, then you have 6 million, 2 million, 2 million, right? Train, dev, test. And the question is, do you really need 2 million examples to estimate the performance of your final classifier? Sometimes you do. If you're working on online advertising, which I have done, and you're trying to increase your ad click-through rate by 0.1%, because it turns out increasing ad click-through rates by 0.1%, which I've done multiple times, turns out to be very lucrative, then you actually need a very large data set to measure these very, very small improvements. Because to increase an ad click-through rate by 0.1, you might actually have a lot of projects. You might have 10 projects, each of which increases ad click-through rate by 0.01%, right? And so to measure these very small differences in algorithm 1 does 0.01% better than algorithm B, but so you need a lot of data to tease out that very small difference. So if you're in the business of teasing out these very small differences, you actually need very large test sets. But if you're comparing different algorithms, and one algorithm is 2% better, or even 1% better than the other algorithm, then with 1,000 examples maybe, right? 1,000 examples may be enough for you to distinguish between these much larger differences. So my recommendation for choosing the def and test sets is choose them to be big enough that you have enough data to make meaningful comparisons between different algorithms. And if you suspect your algorithms will vary in performance by 0.01%, you just need a lot of data to distinguish that, right? So if you have 100 examples, then if one algorithm has 90% accuracy and one algorithm has 90.01% accuracy, then unless you have at least 1,000 examples or maybe 10,000 or more, you just can't see this very small difference, right? If you have 100 examples, you just can't measure this very small difference. So my advice is choose your dev and test sets to be big enough that you could see the differences in the performance of algorithms that you roughly expect to see. And then you don't need to make your dev and test sets much larger than that. And I would usually then just put the data you don't need in dev and test sets back in the training set. So when you're working with very large data sets, say 1 million or 10 million or 100 million examples, what you see is that the percentage of data that goes into dev and test tends to be much smaller. So it might be, so you see, for example, maybe 90% train, 5% dev and 5% test, right? Or even smaller, or even 1%, depending on how much data you really need to measure to the level of accuracy you need, the differences in the performance of your algorithms. Okay? Cool. All right. Just to give this whole procedure a name, what we just did here between the train and dev set, this procedure that we have is called holdout cross-validation. And sometimes, to distinguish this from other cross-validation procedures we'll talk about in a minute, sometimes this is called simple holdout cross-validation. We'll talk about some other holdout cross-validation procedures in a second. And the dev set is sometimes also called the cross-validation set. So sometimes sometimes you hear people say, we're going to use a cross-validation set. That means roughly the same thing as a dev set. Okay. So in the normal workflow of developing a learning algorithm, when you're given a data set, I would split it into a training set and a dev set. Oh, and I used to say cross-validation set, but cross-validation is just a mouthful. So I think just motivated by the reducing number of syllables, because we're using this concept so often, more and more people just call it the dev set, but it means roughly the same thing, right? So when I'm building a machine learning system, I'll often take the data set, split into train and dev, and if you need a test set, then also a test set. And then keep on fitting the parameters to the training set. and evaluating the performance of your algorithm on the dev set, and sort of using that to come up with new features, choose the model size, choose the regularization parameter like lambda, really try out lots of different things and spend, several days or weeks to optimize the performance on the dev set. And then when you want to know how well is your algorithm performing, to then evaluate the model on the test set. Right? And the thing to be careful not to do is to make any decisions about your model using the test set, right? Because then you're assigned to fit the data to the test set, and it's no longer an unbiased estimate. And one thing that is actually okay to do is if you have a team that's working on a problem, if every week they measure the performance on the test set and report out on a chart, right? The performance of the test set, that's actually okay. You can evaluate the model multiple times on the test set. You can actually give out a weekly report saying this week for our online advertising system, we have this result on the test set. 1 week later, we have this result on the test set. 1 week later, this result on the test set. It's actually okay to evaluate your algorithm repeatedly on the test set. What's not okay is to use those evaluations to make any decisions about your learning algorithm. So for example, if one day you notice that your model is doing worse this week than last week, on the test set, if you use that to revert back to an older model, then you've just made a decision that's based on the test set, and your test set is no longer biased. But if all you do is report out the result, but not make any decisions based on the test set performance, such as whether to revert to an earlier model, then it is actually legitimate. It's actually okay to keep on, use the same test set to track your team's performance over time. Okay? All right, good. So when you have very large data sets, this is a procedure for defining the train, dev, and test sets. And this procedure can be used to choose the model or polynomial. It can also be used to choose the regularization parameter lambda, or the parameter c, or the parameter tau from locally weighted regression. Now, what if you have a very small data set, right? So it turns out that, so I'm going to leave out the test set for now, right? Let's just assume there's some separate test set. I'm not going to worry about that for now. But let's say you have 100 examples, right? If you're going to split this into, 70 in the training set in S subscript train and 30 in S dev, then you're training your algorithm on 70 examples instead of 100 examples. And so I've actually worked on a few healthcare problems. Actually, most of my PhD students, including Anand, are doing a lot of work on machine learning applied to healthcare. And so I actually worked on a few data sets in healthcare where, every training example corresponded to some patient that sometimes had a, unfortunate disease, or if you're working, or if every example corresponded to injecting a patient with a drug and seeing what happened to the patient, right? Sometimes there's literally a lot of blood and pain that goes into collecting every example. And if you have 100 examples, to hold out 30 of them for the purpose of model selection, using only 70 examples and 100 examples, it seems like you're wasting a lot of data that was collected through a lot of literal pain, right? So is there a way to say do model selection, such as choose the degree of polynomial without, quote, slightly wasting so much of the data? There is a procedure that you should use only if you have a small data set, only if you're worried about the size. Oh, and the other disadvantage of this is you're evaluating your model only on 30 examples, and that seems really small, right? Can you just find more data to evaluate your models as well? So there's a procedure that you should use only if you have a small data set called k-fold cross-validation, or k-fold CV. And this is in contrast to simple cross-validation. But this is the idea, which is, let's say this is a training set S. So you have x1, y1, down to x, say 100, y100. What we're going to do is take the training set and divide it into k pieces. So for the purpose of illustration, I'm going to use k equals 5 when I'm just to make the writing on the board sane. K equals 10 is typical. Right? guess, for illustration. But so what you do is take your data set and divide it into 5 different subsets of, in this example, you would have 20 examples. 100 examples divided into 5 subsets, so there are 20 examples in each subset. And what you do is, for I equals 1 to k, train, i.e. fit parameters, on k minus 1 pieces, and then test on the remaining one piece, and then you average, right? So in other words, when k is equals 5, we're going to loop through 5 times. In the first iteration, we're going to train on these and test on the last 1/5 of the data. So we'll hold out the last 1/5 of the data, train on the rest, and test on that. And then in the second iteration, through this for loop, we'll train on pieces 1, 2, 3, and 5, and test on piece number 4, and we get a number. And then you hold out this third piece, train on the others, test on this, and so on. So you do it 5 times, where on each time you leave out 1/5 of the data, train on the remaining 4/5, and you evaluate the model on that final 1/5. Okay? And so if you're trying to choose the degree of polynomial, what you would do is, I guess, for d equals 1 to 5, right? So you do this procedure for a first order polynomial. You fit a linear regression model 5 times, each time on 4/5 of the model, and test the remaining 1/5. And you repeat this whole procedure for the quadratic function, repeat this whole procedure for the cubic function, and so on. And after doing this for every order polynomial from sort of 1, 2, 3, 4, 5, you would then pick the degree of polynomial that, and then for each of these models, you then average the 5 estimates you have for this error, okay? And then after doing this, you would pick the degree of polynomial that did best according to this metric, right? And then maybe you find that the second order polynomial does best. And now you actually end up with 5 classifiers, right? Because you now have 5 classifiers, each one fits on 4/5 of the data. And then there's a final optional step, which is to refit the model on all 100% of the data. Right? So if you want, you could keep 5 classifiers around and output their predictions, but then you're keeping 5 classifiers around. It's maybe a bit more common now that you've chosen to use a second order polynomial to just refit the model once on all 100% of the data. Okay? And so the advantage of k-fold cross-validation is that instead of leaving out 30% of your data for your depth set on each iteration, you're only leaving out 1/k of your data. I use k equals 5 for illustration, but in practice, k equals 10 is by far the most common choice that we use. I've sometimes seen people use k equals 20, but quite rarely. But if you use k equals 10, then on each iteration, you're leaving out just 1/10 of the data, 10% of the data, rather than 30% of the data. Okay? And so this procedure, compared to simple cross-validation, it makes more efficient use of the data because you're holding out only 10% of the data on each iteration. The disadvantage of this is computationally very expensive, that you're now fitting each model 10 times instead of just once. Okay? But when you have a small data set, this is actually a better procedure than simple cross-validation. If you don't mind the computation expense of fitting each model 10 times, this actually lets you get away with holding out less data. All right. And then there's one even more extreme version of this, which you should use if you have very, very small data sets. So sometimes you might have an even small data set. if you're doing a class project with 20 examples, that's small even by today's machine learning standards. There's an extreme version of k-fold cross-validation called leave one out cross-validation, which is if you set k equals m, right? So in other words, here's your training set, maybe 20 examples. So you're going to divide this into as many pieces as you have training examples. And what you do is leave out one example, train on the other 19, and test on the one example you held out. And then leave out a second example, train on the other 19, and test on the one example you held out. And do that 20 times, and then you average this over the 20 outcomes to evaluate how good different orders of polynomial are. The huge downside of this is computationally very, very expensive because now you need to train your algorithm m times. So you kind of never do this unless m is really small. I personally I pretty much never use this procedure unless m is 100 or less, I guess. If your model isn't too complicated, you can afford to fit a linear regression model 100 times. It's not too bad, right? So if m is less than 100, you could consider this procedure. But if m is 1,000, fitting a model 1,000 times just seems like a lot of work, then you usually use k-fold cross-validation instead. But if you do have 20 examples, then I would then if you have 20 examples, I would probably use this procedure, and somewhere between 20 and 50 is maybe when I switch over from leave one out to k-fold cross-validation. Okay, yeah.
In k-fold cross-validation, could we use the fact that we run this k times to build or to find the variance of our measurements of error, and then have some sort of confidence intervals?
Oh. Yeah, so, right. So since you have k estimates, say 10 estimates, you're using tenfold cross-validation, can you measure the variance on those 10 estimates? It turns out that those 10 estimates are correlated because each of the 10 classifiers, 8 out of 9 of the sets of data they trained on overlap. So there was some very interesting theoretical result. There were some research papers written by Michael Kearns, actually. It was like a long time ago, trying to understand how correlated are these 10 estimates. And from a theoretical point of view, as far as I know, the latest theoretical result shows that this is not a worse estimate than training error. But maybe short answer in practice is not. You could measure it, but we don't really trust that estimate of variance because we think all 10 estimates are highly correlated, or at least somewhat correlated. Yeah. Yeah. Go ahead. Whether I recommend using k-fold cross-validation deep learning. If you have a very small training set, then maybe yes, but deep learning algorithms depend on the details, right? Sometimes it takes so long to train that training a neural network 20 times, seems like a pain unless you have enough data, unless your neural network is quite small, right? Yeah, so it's rarely done with a deep learning algorithm. But if you have frankly, if you have so little data, if you have 20 training examples, there are other techniques that you probably need to use to boost performance, such as transfer learning, or just more hand engineering of input features or something else. Right? Yeah. Sorry, say that again?
Does the average step at the end of the algorithm literally mean averaging the weights you found?
Oh, sorry. Thank you for asking that. This average step, no. I meant averaging the test errors. So here, you will have trained 10 classifiers, and when you evaluate it on the left out 1/10 of the data, you get a number, right? So you're looping 10 times, hold up one part, train on the others, test on this part you left out, and so that will give you a number. Like it'll say, oh, when you test on this part you left out, the squared error was 5.0, and then you do it again, squared error was 5.7, squared error was 2.8. So by average, I meant average those numbers. And the average of those numbers is your estimate of the error of a third order polynomial for this problem. Make sense? So this is averaging the set of real numbers that you got from this. So this loop gives you k real numbers, and so this is averaging those k real numbers to estimate for this outer loop how good a class 5 with that degree polynomial is. Okay, wow, actually a lot of questions. There's one thing I want to cover. Go ahead. There's last two, go ahead.
If you were interested in something other than just like the accuracy, like maybe like the F1 score or like recall, would it make more sense to do something that, other than just average them from all the different sets? Like,
I see, sure. Yes, if it's something other than F1 score, would it do something other than average? Yes, it would. Averaging F1 score is complicated, yes. I think we'll talk, actually, so this week, Friday, we'll talk about learning theory. Next Friday, we're talking more about performance evaluation metrics. So actually, I'm going to talk about F1 score. All right, Mitch, one last question?
how do you sample the data in these sets?
Oh, sure. How do you sample the data in these sets? So for the purpose of this class, assuming all your data comes to the same distribution, I would usually randomly shuffle. Again, in the era of machine learning and big data, there's one other interesting trend, which just wasn't true 10 years ago, which is we're increasingly trying to train and test on different sets. We're trying to train on data collected in one context and apply it to a totally different context, such as we're trying to train on speech collected on your cell phone because you allow that data, and trying to apply it to a smart speaker where it was collected on a different microphone than your cell phone or something. So if you are doing that, then the way you set your train depth test split is a bit more complicated. I wasn't going to talk about it in this class. If you want to learn more, I think at the start of the class, I mentioned I was working on this book, Machine Learning Yearning. So that book is finished, and if you go to this website, you can get a copy of it for free. That talks about that, and I also talk about this more in CS230, which goes more into the big data. But you go and learn machine. You can also read all about it in machine learning yearning, if the training test sets are different in distribution. Yeah, but random shuffling would be a good default if you think your training test sets aren't too different. All right, just one last thing I want to cover real quick, which is feature selection. Right. And so, so let me just describe one. So sometimes you have a lot of features. So actually, let's take text classification. You might have 10,000 features corresponding to 10,000 words, but you might suspect that a lot of the features are not important, right? You know, the word the, whether the word the is called a stop word, whether the word the appears in an email or not, doesn't really tell you if it's spam or not spam, because the word the, these are called stop words. They don't tell you much about the content of the email. But so if there are a lot of features, sometimes one way to reduce overfitting is to try to find a small subset of the features that are most useful for your task. Right? And so this takes judgment. There are some problems like computer vision where you have a lot of features corresponding to there being a lot of pixels in every image, but probably every pixel is somewhat relevant, so you don't want to select a subset of pixels for most computer vision tasks. But there are some other problems where you might have a lot of features, and you suspect the way to prevent overfitting is to find a small subset of the most relevant features for your task. So feature selection is a special case of model selection that applies to when you suspect that even though you have 10,000 features, maybe only 50 of them are highly relevant. Right? And so one example, if you are measuring a lot of things going on in a truck in order to figure out if the truck is about to break down, right? You might, for preventive maintenance, you might measure hundreds of variables or many hundreds of variables, but you might secretly suspect that there are only a few things that predict when the truck is about to go down, so you can do preventive maintenance. So if you suspect that's the case, then feature selection would be a reasonable approach to try. Right? And so here's I'll just write out one algorithm, which is start with, this is script f equals the empty set of features. And then you repeatedly try adding each feature I to f and see which single feature addition most improves the depth set performance. Right? And then step 2 is go ahead and commit to add that feature. To F. Okay. So let me illustrate this with pictures. So let's say you have 5 features, x1 through x5, and in practice it would be more like x1 through x500 or x1 through 10,000, but I'll just use 5. So start off with an empty set of features and train a linear classifier with no features. So the model is h of x equals theta 0, right, with no features. So this won't be a very good model, but see how well this does on your depth set. So this basically will average the y's, right? So it's not a great model. Next, so this is step 1. In the second iteration, you would then take each of these features and add it to the empty set. So you can try the empty set plus x1, empty set plus x2, empty set plus x5. And for each of these, you would fit a corresponding model. So for this one, you'd fit h of x equals theta 0 plus theta 1 x5. So try adding one feature to your model and see which model best improves your performance on the depth set, right? And let's say you find that adding feature 2 is the best choice. So now what we'll do is set the set of features to be x2. For the next step, you would then consider starting with x2 and adding x1 or x3 or x4 or x5. So if your model is already using the feature x2, what's the other feature, what additional feature most helps your algorithm? And let's say it is x4, right? So you fit 4 models, see which one does best, and now you would commit to using the features x2 and x4. And you kind of keep on doing this, keep on adding features greedily, keep on adding features one at a time to see which single feature addition helps improve your algorithm the most. And you can keep iterating until adding more features now hurts performance. And then pick whichever feature subset allows you to have the best possible performance in the depth set. Okay, so this is a special case of model selection called forward search. It's called forward search because it's starting with an empty set of features and adding features one at a time. There's a procedure called backward search, which you can read about that. We start with all the features and remove features one at a time. But this would be a reasonable feature selection algorithm. The disadvantage of this is it's quite computationally expensive, but this can help you select a decent set of features. Okay. Sorry about running a little bit late. Let's break. Oh, so I think I was meant to be on the road next week, but because is still unable to teach, I think we'll have Raphael teach decision trees next week, and then also Kian talk about neural networks next week. Okay, so let's break for today, and maybe we'll see some of you at the Friday discussion session.